Hello everyone. Today in this video we are going to solve one question from Jetli, and that is a little long questions, but in this question we are going to learn so many concepts. Okay, so let's start. The question is of non-degenerate perturbation theory and charged oscillator in an electric field. So that example is a particle of charge q mass m moving in a 1D harmonic potential with the frequency omega and is subjected to a weak electric field in x direction. So this is the setup. Then we have to find out the exact expression for energy, and in V we have to calculate the energy to the fast non-zero corrections and compare it with the exact result obtained. Okay. So let's see the thing. Suppose here that charge is q, that particular charge q, and having mass m, and that is in external electric field, that is weak external field is applied. Okay, so due to this applied electric field, that charge is oscillating, and for this the interaction between the oscillating charge and external potential gives rise a Hamiltonian, that is perturbing Hamiltonian. You can see it as QE x cap. Okay, that you know that energy is displacement into force, at Fx and F equal to QE. From this perturbing Hamiltonian arises. Okay, so total Hamiltonian is unperturbed Hamiltonian plus perturbed Hamiltonian, and that unperturbed Hamiltonian is due to the this two term, you know, from very starting of quantum mechanics, that unperturbed Hamiltonian is p square by 2n plus half kx square, as this is a oscillating charge, so potential is half kx square. Okay, and k is the m omega square, that k is the force constant. So total Hamiltonian is this much. So if you put the value, the Hamiltonian is this, and see again the further things is minus h square by 2m d square by dx square plus half m omega square. If you take common, then things will be x square plus this term. See here that Hamiltonian is proportional to x square as well as x. So as here is linear term, so you have to convert it in square term, so that the things we are doing. Okay, and half m omega square take common, then x square plus 2ab, and b we have to take as a b, so b square minus b square, so this will make a square term, x plus qe by m omega square minus q square e square by m square omega to 4. Okay, so this is the total Hamiltonian actually. So if you replace as y, this term to y, then the Hamiltonian is this, and one constant term is subtracted, that is q square e square by 2m omega square. Okay, and see this is the total simply derivation, so you can see it from this video. So I am not explaining in detail, I am writing it totally, so you can see. So our Hamiltonian is this much, and you know this term is on so will give the energy again this much n plus half h cot omega, but here the another term is minus q square e square by 2m omega square. So this total energy eigenvalue of this total Hamiltonian. Okay, and this is the exact energy expression. Here you are not using any harmonic oscillator, a cap plus a cap traverse things are that we are not using, we are simply deriving like this. So See here that in absence of electric field, potential is half k x square. That means the particle is oscillating about the origin in parabolic path. Okay, but in presence of electric field, that potential is perturbed, so the x is changing to x plus qe by k whole square. Okay, so for this the position is quite shifted to left, and then like this, that particle is shifted to left and oscillating about minus qe by x in a parabolic path. Okay, that does not affect our angular frequency as well as time period. That only particle is only shifted, but our time period is remains same as before the unperturbed Hamiltonian. Okay, so this is the exact approximation case. If we try to find out the energy correction by using this, the first order correction to energy is En equal to inner product in between the same state of the perturbed Hamiltonian. Here see the perturbed Hamiltonian is QEX. So the inner product of x in the same state gives 0. Okay, so first order correction gets 0, but there is also another correction, that is second order. So you have to see what's getting second order energy state is sum over m is not equal to n, and inner product in between the different states, and it's the whole mod square divided by en0 minus en0. Okay, so if you see that, you know that in a harmonic oscillator x cap can be written as h cap by 2m omega root whole into a cap plus a cap dragger. Here a cap is lowering operator, a cap dragger is raising operator. Okay, and another thing is if you operate a cap in cat n states, then its value will be root n minus 1 cat. Okay, and if you operate a cap dragger in cat n, you will get that n plus 1 root and n plus 1 cat. Okay, so put x cap here. Here I am separating it in two terms because n can be n plus 1 or n minus 1. So I am taking both terms, so I am separating in two terms. Then I1 is this term. So if you put the value of x cap, then the thing will this, and another thing en0 minus en minus en0 minus en minus 1 0 will keep the value as minus h cut omega. Okay, so put the values and operate a cap and a cap dragger. So the final value of phi1 is this much, and if you find out I2, similarly the final value is this much, and add these two, the final value will be minus q square a square by 2m omega square. This is second order correction term. So the total energy correction is En equal to En0 plus En1 and En2. This term is 0, but this term gives n plus half h cut omega, that is the original energy eigenvalue, and this is the correction. So if you add the equation 1, gets equation 2. So this agrees with the exact energy we found in equation 1. We prove this in two methods. Okay, so the correction in wave function, is sum over m is not equal to n and this much, and put the value of hp, we will get the things like this. This is the extra thing I am adding, the correction in wave function. You can see it by own. So the total sign is ket n plus sin 1, which is the first order correction, and see here ket n is the exact eigenstate of nth excited states. So all the things I said, and maximum things are mathematically, some things are conceptual. You have to keep in mind the thing is, let's I am saying This expression you should have keep in mind because there is some question asking that what is the energy expression after the perturbation. So you can give answer directly. So thank you. I hope you all get my point.